What's going on, everyone? I'm going to make a nice little recording here out of, I guess we're using the Larson calculus book, kind of looking at sections 4.2 and 4.3, kind of combining them really into one section. Looking at definite integrals, Riemann sums, and antiderivatives, kind of all at once. So let's get into it. Some notational things for you as far as Riemann sums go. What we've kind of been doing was finding the area under the curve, estimating with rectangles, LRAM and RRAM. The more rectangles I use, the better my estimate. So if I had an infinite amount of rectangles, that would be the best thing, where the leftover space or the too much space is minimized. That's kind of a limit approach here in pink. If I said that the limit as n goes to infinity, where n is the number of rectangles or subintervals, goes to infinity. So starting with your first rectangle all the way to your last rectangle, and sigma, we're adding all those rectangles up. And the rectangles are always base times height. So the base is going to be the change in x, and your height is going to be the function evaluated for each c of k subinterval, depending on how many rectangles you have. So you're plugging into a function is what you're doing. So it's base times height, add them all up for an infinite amount of them, is the notation for the Riemann sums, LRAM and RRAM. What I want to kind of get away from is doing more of everything you see here in black, which is integration. These are called definite integrals because they have definable starting and stopping points. So you would start at A, you would stop at B. If you're thinking of as driving a car, you started driving your car at noon, you stopped driving your car at 3 o'clock, how far did you go? You can integrate some velocity function to decide that. And it's going to be in this format. You integrate f of x, some function, dx is telling you what the variable is, so with respect to x, and that's going to get you back to the original position function if you're doing velocity. So your upper limit of integration is b, your lower limit of integration is a. That elongated s, summa, I believe it's called, that is your integral sign or your integral symbol. F of x is your function, we call that the integrand. And the variable at which I said you were integrating with respect to dx. You want to think of all that as me giving you the derivative. I'm giving you the derivative. You find the antiderivative to get back to the original function. So you're going to get the original function. You're going to then evaluate it at the upper limit, evaluate it at the lower limit, and then subtract is going to be that process. That in a nutshell is what we're going to try to do to get away from LRAM and RRAM. Sometimes finding the antiderivative is a little bit more involved than others. So I'm going to show you some like little tricks and tips for when you can't find the antiderivative using the reverse power rule. All right, let's get into it here. So for this first question, I'm saying to integrate, this is a definite integral because it has definable starting and stopping points from -2 to +2. The function square root 4 minus x squared with respect to x. Okay, essentially what you're doing is finding the area under that curve from -2 to +2. To find the antiderivative of that, it's a bit of a process. So I'm going to think of this one a little bit differently. I'm going to think of this one as a, like a visual geometric approach. I'm going to go ahead and graph the square root of 4 minus x squared. That should look familiar to you. This has come up several times throughout the year. 4 minus x squared, that's going to be half of a circle. It's the top half of the circle because there's no plus or minus in front of the square root. And it's going to be a radius of 2. If you remember x squared plus y squared equals 4, and then solve it for y, you would have the function square root of 4 minus x squared. So I'm going to go left 2, right 2, and then draw the top half of the circle. And when I'm integrating that function, which is this blue circle, from -2 to +2, what I'm doing is finding the area in yellow. Well, I'm not going to estimate that with rectangles. What I'm going to do instead is just go ahead and find the area of that shape. You remember the area of a circle from geometry class, pi r squared. I'm only finding the area of half a circle, so 1/2 pi r squared. The radius was 2. Conveniently, that's where I was asking you to integrate it from, starting at -2 and +2, the endpoints on the x-axis. So 1/2 pi r squared, 2 squared is 4, And then half of 2, oh, sorry, excuse me, half of 4 is going to be 2 pi. So the area of half of that circle is 2 pi. Therefore, the integral from -2 to +2 is also 2 pi. So there's a geometric approach to something I can't find the antiderivative of. Integrate from -2 to +3 the absolute value of x. I don't know how to find the antiderivative of absolute value of x, so I'm going to go with the same approach. I know how to graph absolute value of x. There's a rough sketch. I'm going to ask you to integrate it from -2 to +3. So what you're doing is finding the area under the absolute value of x between these two sections, a triangle on the left and a triangle on the right of the y-axis. I don't know how to find the antiderivative of absolute value of x, but I do know how to find the area of a triangle back from geometry. The area of a triangle is 1/2 base times height. The base of the triangle on the left is 2 units because I went out to -2. The height of that triangle goes up to the absolute value function, -2, the absolute value of that is +2. So 1/2, 2 times 2. 2 times 2 is 4, half of that is 2. That's the area of the triangle on the left. The area of the triangle on the right, 1/2 base times height. Base is 3, height is 3. 3 times 3 is 9. Half of 9 is 4.5. If I'm integrating, I would be then combining these two together, and I'm going to add them and get 6.5. The area is 6.5, and then the integral is also 6.5. The area and the integral don't always equal each other. I'll explain that in a moment. Both of these triangles have positive area because they're both above the x-axis. And in this situation, the area and the integral are the same. Integrate x with respect to x from -2 to 3. Okay, this one I could find the antiderivative of. Let me do a geometric approach, and then I would do the antiderivative and then evaluate using that approach. So graphing. If I were to graph x, it's just a line with a slope of 1 through the origin 0. From -2 to +3. I am asking you to find the area of two triangles. The triangle from 0 to 3 is above the x-axis. That's going to have a positive area because it's above the x-axis. The triangle from -2 to 0 is below the x-axis. That green triangle is going to have a negative area. If you're thinking of this in terms of a velocity in a car, think of this as driving backwards. You can drive backwards, but you would still have a positive amount that you drove. Okay, so to integrate, I'm not finding the total area. I'm finding the difference between these two areas. The area of the triangle on the left in green, 1/2 base times height. 2 times 2, 4, half 2. It's below the x-axis, so it's negative. The area of the triangle on the right, 1/2 base times height, 4.5. Positive because it's above the x-axis. The integral is the net change, the difference of these two numbers. -2 plus 4.5 is 2.5. However, the total area would be the absolute value of both of those added up, 6.5. The total area in this situation is different than the integral from -2 to 3 because part of the shape, or I shouldn't say that, part of the function is below the x-axis, part is above the x-axis. The integral is the net change. Think of this as driving backwards for 2 minutes and then driving forward for 3 minutes, but going the same speed, you have advanced 2.5. Integrate x with respect to x from -3 to +3. Oh, pause on this question. Let me go back. I forgot. I told you I was going to do the last problem, a different technique. Then I forgot. I got excited. I apologize. Okay. Suppose I didn't want to draw the picture. Suppose I want to just go ahead and find the antiderivative. The reverse power rule adds an exponent and then divides by that exponent, so 1/2. If you took the derivative of what you see here in blue, you will get the equation for y equals x. So the power rule would always say, take this 1, bring it down, multiply, and then subtract. So you multiply, then subtract the exponent. Do the opposite in the opposite order. Add 1 to the exponent and then divide is the antiderivative for the reverse power rule. Then you are going to evaluate that from -2 to +3. So you're going to evaluate the upper limit. You're going to go 1/2, 3 squared. Subtract the lower limit, 1/2, -2 squared. 3 squared is 9 times 1/2 is 4.5. -2 squared times 1/2 is 2. 4.5 minus 2 is 2.5, which is what I originally said. So there is the practical application of integrating using antiderivatives and then evaluating versus a graphical approach. Still noting that the total area is different than the net change. So this one you drove forward more than you drove backwards. That's why there's a net change of a positive value. But you still drove a grand total of 6.5 if you want to think of it in terms of driving a car. Okay, now going back to question 4. Integrate from -3 to +3 for x. I want to graph it. Y equals x is a slope of 1 through the origin 0, 0. And I'm asking you to evaluate it from -3 to +3. So you are finding 2 region areas, 2 triangles. From -3 to 0, you would have below the x-axis, that is going to be a negative net change. From 0 to 3, the triangle above the x-axis in yellow, that is going to be a positive net change. These 2 triangles are the same shapes. They are both 1/2 base times height, 4.5. The yellow one, 1/2 base times height, 4.5. The green triangle is below the x-axis, so it should be negative. When you combine them, you will get 0. That is the total net change, which is the integral. Now the total area is different from that. It's 4.5 plus 4.5, a grand total of 9. So think of it back to this, driving a car. I like to go back to this because it makes sense to me. I drove a car the same speed backwards and then went forward. I'm in the same spot as where I started. I've gone nowhere. I'm at 0. Or for those of you that are runners that run around the track, you start at the start line. You run all the way around the track. You stop at that same start line. You ran 400 meters, but you've gone nowhere. So your net change is 0. That's a good example as well. Running around the track, a net change of 0. You started where you stopped, but you ran 400 meters. For those of you that are weightlifters, you picked up 100 pounds off the floor, you set it back down. Where are you? Nowhere. You've done nothing, except you have done work because now you're breathing hard. There's a difference between net change and total area. This one, if you wanted to do it as an avoiding all this graphing, because you can find the antiderivative of x, so you would add 1 to the exponent, divide by that, and then you're going to evaluate that from -3 to +3. So you're going to plug in the upper limit, subtract the lower limit being plugged in, and when you work all that out, you will get 0, even though you have a total area of 9. Okay, integrate from 0 to 3 for the function x squared dx. Let me do this one graphically. X squared is a parabola. From 0 to 3, I am asking you to find the area you see in yellow. That is not a geometric shape that I can have a formula to take the area of. That's not a triangle. It's got a curve on it. So I can't do 1/2 base times height. I don't want to estimate this with rectangles. I'm trying to get away from LRAM and RRAM and Riemann sums. Okay, so I cannot do this with a graphical geometric approach. I have to use the antiderivative. The antiderivative adds 1 to the exponent, and now I divide by that number. Divide by 3 is the same thing as multiply by 1/3. Take the derivative of blue, you will get black. The antiderivative adds 1 and divides by it. It's the reverse of the power rule. That you will now evaluate from 0 to 3. This bar that I wrote is the evaluation symbol. So evaluate the antiderivative from 0 to 3. So you are going to plug in the upper limit first. Then you're going to subtract from that, plugging in the lower limit. 3 cubed is 27. 27 times 1/3, 9. 0 cubed is 0, times 1/3 is 0. 9 minus 0 is 9. The total area is also 9. When the entire function is above the x-axis, like you see here, the total area and the net change will be the same. -2 to 0 for x cubed. Okay, the visual that goes along with this one. X cubed is a function that looks like this. That I'm asking you to evaluate from -2 to 0. So from there to there, I'm asking you for this area in green. Again, it's not a geometric shape that I have a formula for, so I have to find the antiderivative. Add 1 to the exponent. Divide by that exponent. Evaluate it from -2 to 0. Plug in the upper limit first. Minus, you're finding the difference between where you stopped and where you started. Plugging in the lower limit. Zero to the 4th is 0 times a 4th is 0. -2 to the 4th times a half, and then we're subtracting all that would be -4. The net change is the integral -4. Notice it's negative because it's below the x-axis. The total area is +4. So this is like you drove the car backwards to -2. You went back in time. How far did you go? I went backwards 4. How far did I go in total? 4 miles or whatever. All right, I got some properties of integrals I want to talk about. Kind of got them highlighted here. I'm going to move these away as I talk about them. There's these 5 that we need to know. Here's the first one. Order of integration. And if I go too quick, you can just hit pause at any point here and then write down what you need to write down. But try to listen to me and not write at the same time. The order of integration. These look exactly the same, except I did one little thing. I switched where A and B were. I switched the order of integration. The lower limit and the upper limit switched. If I do that, you have to change your answer to negative. So if I went back to the previous problem that I just did, one of the previous ones, I just did, I integrated 0 to 3 for x squared dx, and I got 9. If I were to reverse the order of integration from 0 to 3 to switch it to 3 to 0, then my answer is going to be -9. If you run around a track, you run 400 meters. If you run backwards, you now went -400 meters. The next property, the 0 property. Notice the limits of integration are A to A. So you've gone, so no time has passed, you've gone nowhere, 0. If no time has passed, you will not move. Or you can't, well, you know what I'm saying. You can't move. Constant multiple. you have a constant k being multiplied times a function. Before you integrate, you could pull that k out in front. You're not really factoring it out. I don't know if that's the right word to use because you're not dividing it out, but you can pull it out on the other side of the integral symbol. Constant multiple property. Sum and difference. You have two functions that are either being added or subtracted. If you want to find the integral, you can separate them and then add or subtract your two individual answers. And then the last one, additivity. If you're going to integrate from A to B and then from B to C for the same function, that's the same thing as integrating all the way through from A to C. Here's an example of that one. You live in Maryland. You're going to drive your car to Pennsylvania. So you could integrate from Maryland to Pennsylvania to see how far you drive. And then you're going to drive from Pennsylvania to Ohio. The distance from Maryland to Pennsylvania and then Pennsylvania to Ohio is the same as the distance from Maryland to just Ohio, assuming you traveled on the same path. Additivity. Okay, a few examples of these. I'm giving you two functions. They're both f of x, so it's the same function. One of them is integrated from 2 to 6, and I don't know what the function is, but I know that the integral is 3. That's the net change. The other function, the same function, f of x, is integrated from 6 to 10. Its net change is 10. I have 3 questions for you. What is then the integral of that function from 2 to 10? Well, if 2 to 6 is 3 and 6 to 10 is 10, you can add them up and get 13. Go all the way through 2 to 10. That is the additivity property. B, integrate f of x from 6 to 2. Well, I'm telling you 2 to 6 is 3. If I switch the order of integration, I have to change the sign of the answer to -3. That is your order of integration property. And then the last one. Integrate f from 6 to 6. Well, no time has gone by. The answer will be 0. That is your 0 property. So I don't have to give you the functions. I don't have to tell you what they are. But if I tell you their answers to their integrals, you can apply the properties. Okay, one last thing. I'm giving you a function. I've already graphed it for you. It's a parabola. My graph is a little bit off, though. I'm going to have to make an adjustment here. I don't know what happened there. X squared minus x minus 12. Find the total area from -4 to 5, the area between the curve and the x-axis. Well, for starters, if I wanted to graph this and I didn't give you the graph, you can factor it. You can calculate the zeros. You can calculate the x-intercepts. Two numbers that multiply to -12 that add to -1 would be -4 and 3. Set your factors equal to 0. You would get -3 and +4. So really this needs to be scooted over a little bit. I'm not sure how that got off. I already made that adjustment. So -3 and +4. I am asking you to find the total area from -4 to 5. In this problem, I am looking for the area of 3 combined regions. That one in yellow, this blue one, and this green one. I cannot integrate x squared minus x minus 12 because the integral and the total area are going to be different. All of this blue region is below the x-axis. It's going to have a negative area or a negative value for an integral. So I have to integrate all 3 sections and then add them up to answer the question of finding the total area. All right, let me do that one with you then. So this yellow section, I have to integrate from -4 to -3 for the function x squared minus x minus 12. I apologize for the messy handwriting, dx. To do that, I'm going to find the antiderivative of that trinomial. The antiderivative of x squared add 1 to the exponent, divide by it. Minus, add 1 to the exponent, divide by it. Minus, add an x, I need a variable. Evaluating that from -4 to -3. Everything in gray is the antiderivative. Now I'm going to evaluate it to try to find the area of everything in yellow. So 1/3 x, the upper limit is -3. Cubed minus 1/2 x, -3 squared minus 12 times -3. I should probably put brackets around all that. Minus the lower limit. Oh, I did that backwards. I have my numbers backwards here, -4 to 3. No, I did, I'm good. Okay, minus brackets. 1/3. Plugging in -4 cubed minus 1/2. -4 squared minus 12. Plugging in -4. All right, for time-saving purposes, using a 4-function calculator to calculate all of that, you will get 3.83. So the area of everything in yellow is 3.83. Now I'm going to do the blue section. I'm going to integrate from -3 to +4 for f of x with respect to x. To save you some time here, I'm going to do this exact same process in orange. I would plug in 4 instead of these -3s, and then I would plug in a -3. I'm going to save you time and tell you that it is -57.16. I would get a negative answer because it's below the y-axis. And then the last one in green, I'm going to integrate from 4 to 5, f of x with respect to x. I will get 3.83 again. Find the total area. I need to add these 3 numbers together. Except I need to turn this blue one positive. So technically I need to take the absolute value. So 3.83 plus 57.16 plus 3.83, my total area is going to equal 64.82. Turn that negative area in blue into positive for total area. When I integrated it, I got a negative answer because it was below the x-axis. I'm asking for total area, so I have to think of this as a positive. Okay, that is the answer to the question. If I asked you this, integrate from -4 to +5 for the function x squared minus x minus 12 with respect to x, I would not get 64.82. I would get 3.8 minus 57.16 plus 3.8, which would be -49.5. This is my total net change. This is the integral from -4 all the way through to 5. That's going to preserve the sign of everything in blue. There's more blue than there is yellow and green, so the negative blue outweighs the yellow and green, which is why my answer would be -49.5. The total net change is not the same as the area if part of that area is below the x-axis. Let that sink in. Hopefully that makes sense. I'll repeat it. Integrating it straight through from -4 to 5 does not answer the question of finding the total area. You have to break it down into 3 sections and then integrate each section individually, take the absolute value of all those integrals, and then add them up. If you're driving a car, you drove backwards more than you drove forward, and that's why you have a total net change of -45. You drove backwards for a little bit, you drove forward for a lot, and now you backed up a little bit more. Your total net change is you've driven backwards more than you've driven forward. All right, guys, that is pretty much it. That kind of sums up antiderivatives along with definite integrals. These are all definite integrals because they have definable starting and stopping points. Getting away from Riemann sums. Hopefully that all makes sense. If not, you could watch this as many times as you want and kind of go through the problems working them out on your own and then watch me work them out. All right, guys, good luck with all that. I'll see you next time.